We want to share with you the way how InnoCube was developed and this important moment to bring into space. We will give you a quick overview of the development of the mission, and then you also want to watch the live event, the stream of SpaceX together with you. You can use the chat for questions. We will try to answer them when there's time. And I also want to greet the persons who are in person here, especially our friends and funding from the DLR. Dr. Michael Brockkamp is here. Thank you.
Hello, everyone.
And our other friends. And also I want to acknowledge some people who helped us during the whole process, during the whole 4 years of development. There is, of course, the funding of the DLR, of the Ministry of the InnoSpace Masters program of the DLR was one of the initial, important funding or opportunities for us, and it's still ongoing, a nice competition. So I think it's currently running. So join for this if you are a research institute and try to have some ideas like our InnoCube. And then we have some partners who helped us developing our payloads. The Institute of Particle Technology in Braunschweig helped us with the development of Wally. Thank you very much, Daniel, for your support during the years. And then I want also to thank some sponsors who provided us with software, Wally Space and the Esatan tool. Thank you that we could use it for our system engineering tasks. And I think that's my greeting. We will now hand over to Professor Stoll of the Chair of Space Technology of TU Berlin, who gives you a quick overview of the Institute. Thank you.
Thanks, Benjamin. Okay, and welcome everybody. It's my pleasure to be here and welcome you to the Chair of Space Technology at TU Berlin. So we are here at Berlin. We are at the Mission Control Center. It's not the first time that we are launching a satellite and operating it from here. So welcome everybody. My name is Enrico Stoll and I'm holding the chair here at TU Berlin. At first, I would like to give you a short overview what we are doing here in general, and then having some specific missions from the last years, and then go to the InnoCube itself. So how is our research arranged at the Chair of Space Technology? We do have 3 groups. One of them on the left side, as you can see, is doing exploration propulsion, which means that we are having a closer look at the moon and how we can use the resources on the moon. Basically, it's only regolith, so the ground powderish stuff you see there, maybe some rocks, maybe some powder. That's regolith. That's the only thing basically you have on the moon, and we're trying to figure out how we can use it for doing some kind of 3D printing, maybe with a mobile rover, maybe with a laser, so on and so forth. The second group that we're having in the middle, which you see there, is the Distributed Space Systems group. This is where all the magic happens, where all the satellite development is taking place. You see there are a couple of older satellites. You see our Mission Control Center there, and there we are doing the development of the satellites. And the third group that you were seeing here is the Small Satellite Rendezvous and Robotics group, and we are basically working on equipping robotic technologies to very small satellites, because we think that is the key to future robotic on-orbit servicing, for example, inspecting a satellite or maybe rendezvous with the satellite for maintenance, for repair, maybe exchanging some old payload systems, something like this, or even active debris removal. This is the focus of the 3 groups, but we are today here to celebrate, or first to launch the InnoCube, and this is in the row of some old satellites, which you can see here on the right side. Those are all of the missions which were launched starting in 1991 with Professor Renner, then Professor Breeze, in the 2000s followed him, and as a matter of fact, now there are 30 satellites already launched and successfully developed here at TU Berlin. So the InnoCube, in cooperation with the colleagues of Würzburg, will be number 31. We had a couple of small satellites, we had a couple of larger satellites in the past. Lately, so within the last 3 or 4 years, we had everything between 375 grams and 22 kilograms. And before this, there were constellation and swarms involved. And we are currently also preparing a experiment for the lunar surface. So what happened in the past here? I would like to give you just 2 examples, what kind of satellites we were building, which we were monitoring and operating in the past. So this is the TU Berlin infrared nanosatellite, the TUBIN. So as the name suggests, it's about infrared, about detecting thermal hotspots, maybe wildfires. So it's a demonstration of wildfire detection with infrared microbolometers. If you have a look at this of the satellite here, there is something like a golden binocular which you're seeing there. This is basically the thermal infrared bolometers, and in the middle, right between them, this is a visual camera. And using the 2 of them together, we can do what you see there in this little GIF, this animated pictures there on the upper right side. We can basically have a look on cloudy, on smoky images, and then with the infrared part, we can detect hotspots of fire, some kind of thermal anomalies there. So this is what we were doing in the past. It was launched in 2021, and in 2023 the TUBIX platform was launched, or the TUBIX 5 platform-based NanoFF mission, NanoFF for nano satellite formation flight. As you know, nano satellite is everything between 1 and 10 kilogram. The FF stands for formation flight. So this is one experiment with 2U satellites. So we have 2 satellites, and both of them are 2U, so basically 2 liters each. And we would like to do an experiment, or we're still doing experiments there with 2 satellites. We would like to figure out how we're doing close proximity operations, how we're coming very, very close to each other. And this is more or less a stepping stone for us to develop very small satellites and being capable of talking to each other. Maybe in the future, maybe with a follow-up mission there. So this is the NanoFF satellites, but we are interested today in our InnoCube. And this one is basically based on a couple of experiments and how everything started. And here I was looking for a very, very old slide. This is basically a slide from 2016, 2017 approximately, where we're introducing or suggesting a volley payload for satellites. And there we were saying, well, the energy storage basically in satellites could be enhanced if we are using the structure of the satellite as well. This little GIF here this little animation should emphasize this one. The idea was to use the volume of the structure of satellites, enhance it with battery or energy storage capabilities, and then basically have a structure which is more or less a battery as well. That was an idea which we were proposing to the InnoSpace team. Fortunately, they were liking it, and the end, or the finish is now more or less of this journey. We were developing this one, we were developing the InnoCube, and fortunately there was another InnoSpace master, the colleague Sergio Montenegro, had another very, very beautiful idea to do an experiment which is called Skip the Harness, SKITH, meaning that we don't have any harness anymore aboard the satellite, which is for communication, so wireless communication, and both of those potential payloads were very, very successful. And after a while, the colleagues of the InnoSpace at DLR meant that it would be worthwhile and interesting to join the forces and build a satellite. And the satellite you can see there in the middle now, which is our little InnoCube. You will have a couple of more information about the SKITH, the harness payload, and about the satellite itself later on. I would just like to emphasize the top of our satellite. So there is a little retroreflector there as well, which belongs to another experiment where we have an onboard navigation experiment. And as a matter of fact, we are currently building an optical ground station here at TU Berlin. or with TU Berlin, but at DLR Neustrelitz, so we can do our own satellite laser ranging. So there is the possibility later on to support the our experiment even more and have other people maybe joining the force and use this as well. And with this little episode here, the episode that I was talking about and the experiment, I would like to come to a conclusion. And thank you very much for joining us, for tuning in today. And yeah, let's keep our fingers crossed. See you later. Bye.
Thank you, Professor Stoll, for this nice presentation. And yeah, I want also, without further ado, give Sergio Montenegro the opportunity to explain the great idea behind SKITH, and of course, before also what the research in the University of Würzburg is at the Chair of Aerospace Information Technology. Yeah, there's some. Here.
Where is the presenter? Okay, thank you. Greetings. Here's a second, please. No.
Next one? Yeah.
Okay, that's we. We are Aerospace Information Technology from the University of Würzburg, and that's what we are doing. We are doing Aerospace Information Technology. First, I would like to say, who are we? You can see here some of my people. 4 of them are here for InnoCube. I am here, and one is missing in the pictures. But as you can see, we are much more than just InnoCube. InnoCube is a very nice and important project, but we are doing so many different things. What we are doing, our emphasis is designed to survive, so ultra-high dependability. What we want is to build machines which are able to survive very adverse situations. And what we are doing is something different than normal approaches. We want to do ultra-fast recovery because we know every computer, every device will fail. So it's not important to try to avoid failures. The most important thing is to be able to recover. And that's what we want, to be able to recover in less than 1 second. And that is what we can do. The next thing is, the computer is not the most important thing. The most important thing is the network. Even if you cannot see it, even if it is wireless, what we are doing now in InnoCube. The next thing is, complexity is very dangerous. So what we are trying is to reduce the complexity to the minimum. We are doing irreducible complexity. So everything which we don't need has to be removed. And the next thing is, we can avoid if something is changing, if something is failing, we have to adapt. So we want to do adaptability, very fast adaptability. And this is one example of the history which we have been done. The beginning was many years ago with these 3 satellites, BIRD, TET, and VIRUS. In these satellites, we used to have 4 board computers. 2 were working and 2 were sleeping. And one was controlling the satellite, and the other one was supervising. And if something fails, we just switch. This was the beginning. Then we did something experimental, the Vidana network. This was not 4 or not 2, but many, many computers. We have a network of 20 of them, and computers can be turned on and off according to what is working and what has failed, so we can move in this network. If some computers are failing, then we can move the task to other computers, so we are moving in the network. We have something which we call floating tasks. So we move where we have computing power. And this is what we are doing now. We are trying to find the most simple solution to provide a computation even if we have failures. So we have developed this very simple switch, which is what we call the keep-off switch. 2 computers are in charge. One is working and the other has to be waiting until the other fails. So what we do is, the one who is working keeps the other sleeping, sending a pulse, wait, wait, wait. If this pulse doesn't come, the other will be turned on, and the other will turn the failed computer off and will take control. So I think this is the most simple solution to have the control with 2 computers. One is working and the other is waiting until we have a failure. I said we are trying to have very high adaptability. that is a very nice example which we are doing. For the next level, what we are doing with InnoCube, after we make the commissioning phase, we want to make learning attitude control. So this is a neuronal network which we install later in InnoCube, and then it will control learning if something has failed, if the performance of wheels have changed, and then it will adapt and continue working. We are doing something similar, not only in space, but on ground. So we have developed some drones which are able to learn how to fly, how to reach new rooms, and move around these obstacles. And going to the other topic, for ultra-fast recovery and very simple software, what we have done is a very simple operating system. Its name is Rhodos. And this Rhodos is able to provide all services which you need for control a satellite, even launchers, drones, and underwater vehicles, which I'm going to show next. And everything is reduced to the minimum, so the whole operating system and communication layer is less than 4,000 lines of code. And this is, I think, a record in the world. And this is the communication layer of this operating system. We have a publish subscriber system implemented, and we can divide the complex applications in very simple applications which are going to communicate using this middleware. You can publish messages, and anyone can subscribe and get these messages, even if it is running on other computer, or maybe some applications are running in space. Then we are going to a gateway to the ground, and all other applications are working here on ground. So for the applications, it makes no difference if the communication partner is in the same computing, in other computer in the same satellite, or even different satellites, or even in space and on Earth. And now I wanted to show you some examples of the things which we are doing. So you can see we have many different projects going from underwater to moon to space. And here maybe you can recognize this room. This is here in the Technical University of Berlin. This is because this is not the first time we are working together with the Technical University of Berlin. So our software is in many satellites of the Technical University of Berlin. Maybe you don't know it, but we are there. So beginning from the BitSats, TechnoSat, Tubin, SNet, and who knows which other satellites, but we have been working with the Technical University for years. And now let me see the different types of projects which we are doing. I said before, we are very deep undersea, 5 kilometers underwater, and this was a glider, the control of this glider, which we have developed. It doesn't have propellers, it's just gliding down and gliding up on the water, able to go up to 5 kilometers underwater. Then going a little bit deeper, here under your feet, we are developing a system with a network, some drones which are able to fly in the sewer system of the black waters of the city and make inspection. Then going a little bit higher, we have some drones which are able to fly autonomously in rooms. A little bit higher, we have drones which are able to find and catch enemy drones for protections. And then going a little bit higher, we have these devices, this foil, which is able to detect cracks and modification in the surface of, for example, surface of aeroplanes. Then we have working with electro aeroplanes, so going higher, but I can say it doesn't help. Electro aeroplanes is not what we are expecting. And now a little bit higher, we are making the avionics for launchers, and a little bit higher, we are working in satellites, for example, the InnoCube, which we are going to see today, and higher, we were almost on the moon. We have programmed and developed the avionics of this rover for the moon, but it's a pity if the company went bankrupt before they paid. And then we are working on navigation for Mars explorations. So you can see we are going from very deep on the ocean to very far away in space. We cover everything. And something very special, we make technology export. So technology which have been done for space or for aerospace, we try to use it in different terrestrial applications. This is a very nice example. Our drones are able to fly to see where is a door, to see where are obstacles, and fly through. Now the idea is to do the same for blind people. So we are doing acoustic navigation, for example, and peep tone in stereo, which the blind people can follow. And this device will detect where is a way, where are obstacles, and why the people to go through doors, even if they cannot see them. And then we are already working on docking space. This is a DLR project, which we are building 2 satellites, which shall find each other in space, come together, and dock. But now, what we are doing in InnoCube, this is SKITH. It was mentioned before, skip the hardware. And skip the hardware, skip the, the harness. If you can see where is SKITH, you will see you cannot see it. You cannot touch it. You cannot place it in a box. It's there, even if you cannot see it. It's there and it controls everything. This is the communication network which we are doing. The idea is very old. It was the winner of this InnoSpace Masters. If you see, it was almost 10 years ago. So it was a very long way from the first idea until today where we are going to space. So almost 10 years. Okay, and what is the reason for a SKITH? If you see, the problem is the harness. So harness is one of many problems. It's heavy, it's complex, you have many different plugs, many different protocols, and many wires, and you can make a lot of mistakes. And even if you don't mistakes, they can break with movements or something like this. So for satellites, it's almost 10% of the weight invested in wires. And when you are going to the integration, at least 50% of the effort for the integration is with wires. So if we can eliminate this, we can make a very big, much more faster satellites. This is an example for big satellites. If you have a small satellite, okay, you can take it in hand and make the connections downstairs. But if you have a big satellite, you have to fly in order to make the connections on the top of the satellite, which is very difficult and costly. And the same problem is not only in space, we have similar problem in aeroplanes. For example, an A350 had about 470 kilometers of wires. It's nothing new. The aeroplanes industry is already thinking how they can make the communication using wireless. And maybe we can help in this direction. And the problem is not only in aerospace, we have the same situation in cars. So we have the cable tree of cars. It's very heavy and it's very costly too. And it's very prone to failures. For example, the doors, if they are open and closed, these wires are going to break someday. Okay, and what is the solution? The solution is, you know what to do with the things which are making problems. Eliminate them. Okay, if the harness is making problems, well, we eliminate. And the problem is, so do not install wires is very simple. But to do the same with a wires is simple too. It's not more difficult. So we can do it. And let's see, here on Earth, it's already done. This was several years ago. A normal telephone network, many years ago, looked like this. And now it disappears totally. Now you have wireless. So you can have much more telephones. So many telephones like you have now, it will be impossible to do the same using wires. And it's much more easier to install. Then we are going to do the same. 20 years ago, with the telephone network, we went from here to here. Now it's time to do the same with satellites, going from here to here. Eliminate all these wires and make the satellite wireless. Another problem is, if you take a look to your own computer, you will see you have so many different interfaces, and all of them do the same. So you have so many ways to connect your monitor, so many ways to connect your mouse, your keyboard, so many different protocols, I2C, SPI, UART, oh, so many. You can count them with more than 10 of them. And you can do the same, eliminate all these different protocols and use only radio communications. So you don't need wires, you don't need these plugs, and you have only one protocol. And this is what we are doing. Our board computer doesn't have any interface, wire interface to other devices. Any device has only this low power radio communication link. And then you need just to plug, to bring them together. They are going to find each other and communicate. And then you don't have this problem, which protocol going from this to this, or which cable shall I plug going from this to this. It doesn't matter. Just bring all these devices close to each other. They will find each other, and then you will have the communication. And this is the situation in InnoCube. We have many different computers, many for your payload, for your attitude control, for your communication, for your board computer and power. They don't need to be plugged together. Just bring them together, maybe on different tables for the integration to test the satellite. Every engineer has his own system on his table. They are going to be communicating together. You don't need to bring them in the same box, and then you can test everything distributed. So going from this one central computer with many different wires, many different protocols, to this only one communication protocol, no wires at all. This is what we have done in SKITH. And there is something more, something very nice. Maybe if you know Enterprise and these science fiction movies, you will remember this tricorder. If someone is sick or has a problem, the doctor comes when the tricorder makes tick, 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 and then he can say, aha, this is the problem, without making any wires, without making any connections. And we are doing the same. To make a diagnosis of the satellite, we don't need to open or to install any cables. We have another device like any other inside of the satellite. We come close to the satellite, make the analysis, and then we can see what is it doing, how it's going, and if you have to modify something, maybe you don't need to open the satellite, you can do it from outside. Exactly like this, science fiction, but reality in InnoCube. And to demonstrate the real-time capabilities of this protocol, we demonstrate it with a drone, with a quadrocopter. Maybe you know quadrocopters are very unstable. If you have a big delay in communication or in control of the motors, then you will have a crash. And what we did is every propeller has its own controller. Everything is distributed. There is absolutely no central control unit. And they have to communicate and synchronize each other, all other together, in order to be able to fly. And this is what we are doing, using the same protocol, a total distributed control, and this quadrocopter can fly many, many minutes as long as the battery can provide energy, and we have absolutely no crash. So in this case, we can demonstrate the real-time capabilities of this protocol. And that's it. Going from here to here is SKITH. Thank you very much.
Thank you, Professor Montenegro, for this insight and right in time. Next over to you. So now we heard already a little bit of Wally and the InnoCube Masters. And I want to give a bit of a follow-up and a few more details on this technology, which is our second main payload in InnoCube we developed. So we had the slide from Professor Stoll from 2017, so 9 years ago, or no, 8 years ago nearly. And the base idea was bringing capability to the structure of the satellite, and also like doing not the usually liquid lithium-ion battery, but the idea was, a structure is solid, so it will be a solid-state battery. How to bring battery or rechargeable capabilities into the satellite structure. So the setup is technically the same of a battery. You have anode, a cathode, a collector, and the electrolyte, which is usually a liquid electrolyte, and a separator and then you can charge, recharge with the lithium, the active material, and to have the battery charging and recharging. But in InnoCube, we saw this picture already before, or in Wally, we want to implement actually this functionality into the structure. The structure is usually aluminium now, or like in satellites, but also now modern times carbon fiber and carbon reinforced plastics are coming more and more into use. It's used in also aerospace application, and that was the idea. A carbon reinforced plastic is based two-component basically material. You have a carbon fiber, and then you have a resin, and then you have some spaces actually in between. And we were estimated in the initial of the project that we can use some of this volume, which the resin uses, to incorporate some materials which brings you energy storage capabilities. And the idea was like using like the carbon fiber, that's the black lines in the picture, and glass fiber as a separator, and then the solid state electrolyte which connects this, and then conductive materials on the last part. And that's the difference is basically between a rechargeable battery and our battery, and how we really like do it, or like what are the approaches in Wally. Like we have the cathode, which is lithium, I only know the German now, Eisenphosphate, sorry. Then we have a separator. Can be like, we have different approaches also to tune the system. Glass fiber, or you can have a glass fiber with additional impressed separator material to make it a bit more stable. We have the anode, we have carbon fiber with lithium salt and lithium enriched, and that's an electrolyte. We can add additional lithium to raise the capacity. And the solid state electrolyte, it's like the epoxy, or like with lithium salts enriched part. So we have the structure, which is basically a plate of about 2 millimeters thick of carbon fiber. And the goal was like, that was basically what we did in the research of Wally, which was funded through the InnoSpace Masters program. It was a 2 years research to get to this state. And then we started with the InnoCube project. And the goal was how to bring this pre-research, the initial idea, the initial proof of concept, into a real-life application, into the payload of a satellite. So the goal was to characterize this new technology in space, how it will perform, and how it will be characterized. And that is the goal of our mission for Wally, to see how it will work in space in a satellite. So the initial part of the project was we have to transfer this Wally research into this payload application, which is suitable for space, which has then because it's a highly experimental system, has to be separated from the satellite bus and don't compromise the SKITH research basically. So it will have the own power supply, or like has to be supplied as a payload from the bus. We need to characterize the system, discharge and charge all the batteries of Wally in a controlled way, that we can basically do our statistics and see how the charging currents are, how the temperatures are, and how the system behaves over time. And then, of course, we have to produce the system which will fly in Wally. And the basic setup as I told, will be like we have charge regulators which get power from the bus system, which will charge the structural batteries. The sensors will then record the experimental data, and then we discharge the batteries in a controlled way to measure the cycle and then see how it behaves, and can download the data to also do our analysis on ground. And then the important part was during the project how we built this whole volley to space, or volley to space is the payload in the structural batteries. So we needed to do it in a controlled environment. This is a glove box. It needs to do some preparation work. We have pressed the anodes and cathodes together and the materials. Then we had to cut our fiber materials into our shapes we needed. We have to layer it. We have to have then the covers. In the end, we ended up using also glass fiber as cover layer to have some insulation to the satellite structure or to the satellite bus to avoid short circuits and failures. In future, it can be also carbon fiber. And then it had to be cured. And the final product is then the patch, which is a 65 by 65 centimeter patch with a heater on build. That's what you see on the top there. And that had to be implemented in the satellite. So as I told, 65 by 65 centimeters, about 3 millimeters thick with, or 3.5 millimeters thick with the heater on top. The active material inside is roughly a patch by 5 centimeters, so we have a bit additional structure around to have screwing points, and then we have 6 batteries incorporated in the system on the 3 side bolts, and a stack which is incorporated inside as a reference model. And each battery has its own heater that can have also temperature dependency to measures. And the battery itself is a solid state battery that will also help in future to enhance safety of satellite system, because you don't have problems like with lithium-ion batteries, or that they can catch fire easily or explode to overpressure. Their solid-state battery is flame-proof. You have not the pressure changes due to temperature changes. It's very like high-temperature resilient, and also it's safe if it gets penetrated. For example, it may be short circuit, but you will have a thermal runaway like in lithium other cells. And through the battery hardware, of course, we need to control the whole system. Of course, we have our PCB board or electronic or charge electronic, which has SKITH incorporated, because we have no data harness in. Maybe like to mention, but Tom will probably mention it in the system also, there will be power cables, of course, because you can't transfer power wireless yet, unfortunately. But maybe we get to there sometime. So yeah, so we have our charge regulators, our charge electronics. Each cell has its own charge electronics, so we can charge them independently. We have heater control, which is redundant, so can be steered via 2 different systems in case of a failure, that we don't also have like heating all the time on or draining this battery. And we have the current monitoring and recording of the whole system. And then when the satellite is launched and we are starting our scientific experiment, we will operate the batteries, or like we want to get our scientific data. So we will plan the experiment on ground, prepare a command file, because it's like long-term charging the batteries and discharging the batteries, and record the experimental data. So this set will be prepared on ground. We will upload like this experimental plan to the satellite, and then the satellite will execute this command and charge the battery, record the data, discharge the battery, record the data, and finish up the experiment. And after the experiment is done, we will download our experimental data, and then we will do our analysis on ground. And this is the scientific work which we want to do with Wally. And I have some further goals to share, like the mission goal, the overall mission. So I shared already what we want to achieve with Wally. We want to characterize it. Then we have the episode Professor Stoll mentioned about, which is a secondary payload on board, which is a GNSS receiver and the laser ranging system, or the receiver. This is also a payload which was mainly developed with our students, and it's very provided educational use. We have some amateur radio payloads on board, which are developed, and we would talk about later on. We want to improve our education with all the development in both universities of the satellite. We will have had many students involved in the system. Basically, like, yeah, I forgot to update the slide, sorry. It's about 56, I think, students now they involved in this thing. And also we want to have our outreach, and that's also why you are here. So thanks for watching us and also making our research and our more public. And I hope that you like it, and also tell your friends about it. And then I have some facts for InnoCube. Where is InnoCube going? Like, we have the launch later tonight. The orbit will be a 520 kilometer sun-synchronous orbit, which roughly is 97.4 degree inclination. Synchronous orbit is like an orbit which rotates in the same speed as the sun. So the light comes always from the same direction for the satellite when on the same day of time. Then, how long will the satellite be in orbit? So approximately 5.5 years. We did some analysis. So from the start, and then it will decay over time and demise on re-entry. In about 2031. Roughly. So what about space debris mitigation? Yeah, we did the analysis already when the satellite will re-enter, but we had to do also some other analysis to be assured that we are safe and sustainable for the system. So we use the debris risk assessment and mitigation analysis tool from the ESA Drama tool, and so you have to assure that the satellite don't releases any extra debris or causes any further debris and particles than itself in the orbit. So we can assure this because we don't have any pyrotechnics on board, no like lids or caps or anything which we release. So the environment stays clean in this part. Then the second thing is, can the satellite explode, break up? So what could be the scenarios? It could be like explode because you have a pressurized system on board, or liquids or propulsion, which can be act as explosional devices, which the InnoCube don't have. So we can be sure that we don't explode to a failed propellant tank. But also can batteries explode, or failure, any failure basically in the satellite causes some breakup or explosion. But our analysis also, like, we sort of all possible, or hopefully all possible. You only see it when the one thing occurs you never thought of, but we think we have covered all the fronts, so we can't explode. Wally is a safe battery, as I explained. The other battery is very limited in the energy storage. And also no meteorites, micrometeorites can penetrate or will hit, because there's a threshold we don't exceed. So the analyst says we are safe. And that's this 10 by -3 threshold, the potential on-orbit collision risk. And that is our mission goal. Of course, we want to verify that a wireless satellite bus works in orbit, and how the rest of the system is. My colleague from Würzburg, Tom, will now explain you, and I will hand over to you.
Thank you, Benny. Let's see how this works. All right, my name is Tom. I was working on the InnoCube project for the last 4 years now. I will give you a little bit of overview over the systems of InnoCube, over the satellite itself, how it's, which parts are used to build up the whole satellite. I try to cover everything and try not to go into most of the details, so we will not stay here until after the launch. In general, it's a 3U CubeSat, so 1U CubeSat is roughly 10 by 10 by 10 centimeters cube. So we are a 3U CubeSat, so we are roughly 30 centimeters long and 10 centimeters by 10 centimeters. It's a plus CubeSat, which means that we have a little bit of extra space on the top. You can see it on the very top of the satellite where the retroreflector is. So we got the plus sign, we earned the plus sign. Our mass is 4.3 kilograms, so we are quite, it depends who you ask, heavy or not heavy. These are the systems. So when you see the stack of the whole satellite, it consists of different parts of electronic PCBs, which are connected to a backplane system, which I will tell you about later. We have a retroreflector on top. We have a structure made out of aluminum, which contains all the parts. And we have different systems, which I will go into detail right now. So we will start with the power subsystem. Every satellite needs power, so power is available through the sun in orbit. So of course we use solar panels. We have 4 of them on each side, each long side of the satellite. These are SureSpace 3G308 triple junction solar panels from Endurosat. They peak for one of the cells to roughly about 8.4 watts in a 7S1P configuration. These are on the 4 sides, so we get, when we are in the sun, we can recharge our batteries. This is done via the MPPT solar charging controller. We partnered up also with DLR Bremen, who were so kind to develop us the PCBs, which are needed for us to collect all this energy from the solar cells and transfer them into usable power into our electrical subsystem. So this PCB is used for collecting the power from the solar cells. It is also used for controlling the kill switch interface. We have little deployment pins which detect when the satellite is deployed and when it's ready to start operating in space. It also does the battery monitoring and is connected to another PCB. This is the PCDU conditioning and distribution. So we have the solar power, we have some voltage and some amps, and we need to convert them into usable power for our subsystems, for our smaller units, which we have on the satellite. So this is doing the conditioning. It provides 3.7 volts or 5 volts, depending on the unit, and also controls the power lines. So we have different systems which are connected to this PCB, and the PCDU more or less controls these switches. It also acts as a hardware watchdog. Professor Montenegro was mentioning the keep on, keep off relays. So they are incorporated there into hardware, which makes them very reliable because they are very simple designed. And this PCB is also developed by DLR Bremen, especially for our mission. Here's a small overview. I will not go into detail. On the left side, you have the maximum power point tracker with all the systems which are needed for the battery monitoring and the solar charging, and also the isolation switch, which acts as a kill switch. So when we are inside the container, inside the rocket, the satellite will not turn on. It then provides power from the battery and also from the solar cells to our distribution unit, which converts through different DC-DC converters the battery power into usable power for our subsystems, and distributes the power to the different systems. We have two independent power lines for redundancy. So we have a nominal and a redundant power line in case one of them fails. After we collected the solar power, it all goes into a battery, of course. So we will also be able to operate when there is no sun, and also to operate under higher load conditions. We use the GomSpace NanoPower BPX with 12 ampere hours of usable power in a 4S2P configuration with a bus voltage of 7.2 volts normally. That's a quite big battery for our system, which makes us very, we can use the times where we do not have sun very efficiently also for our experiments. To distribute power, we have a wireless data bus system, so we distribute the data using wireless. For this mission, although we plan on doing it maybe in another mission, we do not distribute the power wirelessly, so we'll still have to use some wires, but these are only ground and plus wires, so they are quite simple. Actually, we use the backplane here, so it's like a PCB where they have some connectors where we can insert our modules, and they will be provided power. We do not have main data lines, so we will not do any communication over this PCB bus. There's also no redundant data bus on top of this PCB. We are doing it all wirelessly. This is only for power distribution and some minor GPIO stuff. It also has the two kill switches, which are detecting whether the satellite is in the deployment container or not. So when we take all of this and also the aluminum mechanical structure, we get part of InnoCube. In the middle, we have the battery, the two PCDU, power distribution and conditioning, PCBs inserted into the backplane, and we are ready to insert more modules to have some, to be able to do something with the satellite in the end. So we have the communications subsystem, which of course is necessary for us to command and receive telemetry on the ground. Antenna-wise, we use the Endurosat UHF-3 antenna, which is a 4 monopole antenna configured together. So we have a circular polarized antenna system. It also houses a burn wire mechanism, which after the satellite has been deployed, burns some wires and releases all the antenna rods from the antenna, so we are able to communicate with it. This antenna is connected to two independent GomSpace AX100 transceivers. This is more or less the radio controller, which is able to receive and send signals down to Earth. It uses a maximum power of 1 watts. We are in the UHF spectrum, so we use 435.95 megahertz as our main up-downing frequency with a frequency shift keying modulation, and we have normally 9600 baud rate link to ground. This transceiver is then put onto one of the PCBs which we developed, so our friends at TU Berlin developed. It serves as the interface between this radio transceiver and our own satellite bus. So we have two independent systems of communication. We have the comms A PCB and the comms B PCB, which are redundant and which will switch automatically after some time. these PCBs are necessary to interface with the transceiver to convert the messages into our SKITH wireless data bus. And it's also housing the transceiver switching, so the little switch which switches the antenna depending whichever transceiver we are using. All right, so now we inserted those two PCBs on the very top, which are our comms module, and we have our antenna. Next, we go to the onboard computer. So the onboard computer is generally the computer which is running on the satellite, which is doing data handling and doing computations and so on. So what we are using, actually, because we're using a distributed network of systems, our onboard computer is not the main computer which is controlling everything and which is like one single entity. As Professor Montenegro mentioned, we're using a distributed network system. So the OBC in our case covers our telemetry history and command lists. So when we generate some data, temperatures and so on, actually the OBC will store this history in Flash, and also is able to store command lists which we send up from down from Earth up to the satellite and save these lists so they can be executed in a later time. It also serves as flash storage if we do some data upload. For example, if we do a software upload, we can actually upload it into the free memory space of our onboard computer and then are able to distribute the software to the other nodes to do a software update. So as I mentioned, we are using a different, or as Professor Montenegro mentioned, we're using a different bus system. This is not the bus I'm talking about. So the bus is actually the communication system which we are using to distribute messages and to communicate between the different entities inside the satellite. What we are using here, Professor Montenegro mentioned the general idea of SKITH, the harness. What we are using on InnoCube is a small microcontroller which actually has some HF, so wireless capabilities included. It's running on 2.4 gigahertz in frequency. It's able to use up to 40 channels. We use a frequency shift keying, modulation. We have 2 megahertz bandwidth and 1 megabit per second data rate, which we can distribute between the nodes and are able to use. And it uses a very low power, so only 10 dBm power, which means that when we actually close the satellite and we have all the doors closed of our satellite, the range will be only a few meters for this system. So it's very low power, and also it does not disturb any other systems which are nearby. You can see that the minimal footprint of our SKITH hardware is actually very small. This is the minimal footprint which we can have for our system. It's only 2 centimeters by 3 centimeters, and this is actually the device which is built into every PCB of our satellite, and it actually houses a small PCB printed antenna as well, so we do not need any external components for antenna, which makes it very suitable. And the second nice thing is that it's not only the frequency or the transceiver hardware, but it also houses a normal microcontroller which is used as a computer to do some onboard processing, to calculate stuff, to control stuff. So this is actually a low power ARM Cortex M4 microcontroller from Silicon Labs with 1 megabyte flash and 56 kilobytes of RAM. So it's quite a potent microcontroller. We also added some external flash and MRAM to be able to store more information and more data or programs on the satellite. We only use a very small power because we do not use the transmission continuously, but only when we need to send stuff. So we use very low power. And right now in our implementation, we have 54 kilobits per second at 13 nodes. So the bandwidth actually is right now shared between all the nodes equally, which I will show you in a second. So the basic system is we want to have one orchestrator or one master which tells everybody else what they should do and when they are able to transmit stuff. So we have one SKITH master. This SKITH master is the director for all the other slave nodes on the satellite. So this SKITH master actually is the PCDU, because it's the power distribution unit is required to be on all the time anyways. So we use this as the master as well, because the PCDU actually knows which node is on and off, so it can actually distribute the bandwidth accordingly. Then we can have up to n nodes. In InnoCube we have up to 13 nodes, which can be on in the same time span, more or less, and we can communicate with every actor wirelessly. We do the collision avoidance through a master synchronization, so time division multiple access protocol scheme. It's quite simple, and it's also very flexible and also very robust. That's why we are sending a sync frame in every cycle. In this sync frame, which is sent by the SKITH master, actually it tells every other node at which time they are able to be transmitting. So we assign every other actor in the network a small slot, so there are no collisions on the system. And then starting from slot 1 to up to 13, when the time is right, the other unit will just send its messages, and then after all the messages have been sent, the sync frame will be sent again and again. So this also ensures that when we have some systems which maybe are malfunctioning, we do not spam on the wireless bus. On the one hand, because if we just don't send a sync frame or don't tell this node you can be sending, then they will just not be able to send. And we can also, because the PCDU is actually the master, it can just turn off this node, and then because no power means no wireless transmission, means that this unit will just be off and will not be able to block or cause any problems to the other satellite systems. This is a very nice advantage of this wireless technology, because on traditional, for example, UART or CAN systems, when there's a malfunction, a hardware malfunction in the system, it actually can block all the other actors in the system because it's still physically connected. But on wireless, off means off, no transmission, no problem. Okay, so we added the OBC. Actually now, if we look at the other systems, I told you that all the systems only get power from this backplane, which is on the bottom of the satellite. So the communication through all, between all the actors, the comms node, the PCDU, and the onboard computer, every PCB has this small little minimal footprint I showed you on of this SKITH hardware, and they all communicate wirelessly. Let's go to the attitude determination and control system. The attitude determination and control system is mainly there are two reasons why it's on the satellite. On the one hand, we have this payload, which was already mentioned, episode, where we do the software-defined GNSS positioning. And this has some antennas which have to be pointed towards, not towards Earth, let's put it that way, so they can see the other satellites. And there we need the ADCS system to control the satellite to be pointing this antenna towards open sky and or space. And on the other hand, the retroreflector, which is on the one side of the satellite, also for position experiments, we have to point it directly towards the ground station on Earth and keep tracking it. So this system actually has to be used for this experiment. What we are doing as well, Professor Montenegro mentioned it already, is that we are using the attitude control system in InnoCube for another project where we do machine learning attitude control. So this is actually also serving as the platform for this. We have two redundant ADCS systems which are on one PCB. We have MEMS magnetometers, redundant MEMS gyros for rate detection, and all the determination and control algorithms run on You can see it on the very top right here on the microcontroller and are executed on it. For the determination, we also have 6 wireless sun sensors, which are placed on the outside of the satellite on all 6 sides, which are able to detect the sun vector, the direction where the sun is coming from. There is also a very nice application for this wireless technology, because it makes placement very easy, and actually you can just attach a 9-volt block battery to the sensor and just place it outside of your office on the roof or somewhere, and then you are able to track the sun already. Actuator-wise, we use 3 astrofine reaction wheels for 3-axis controlling, and we have a redundant set of magnetorquers for desaturating and also for controlling the satellite. This whole ADCS system is placed in a dedicated substructure, which makes testing very easy, because we can just put it on on the airbearing table or on test stands, and are actually able to use the same box in different satellites. And because of the wireless capabilities, we just need to provide some power to the PCB, and then the onboard computer or the rest of the satellite of the test model, for example, can sit somewhere else where it's not on the test stand, which makes testing very flexible. Okay, so we put the ADCS box down here for controlling. The satellite is close to complete. We talked about the episode payload. We have the retroflector on top. On the bottom part, I think episode will be talked about later as well. Yes, you will see it a little bit more in detail. We have the antennas here, and we just placed the episode board in the very back here. Let's go further. We have Wally. Wally is this structural battery. We also saw some pictures already. It's placed up here, and also there are batteries in the sides of the satellites, of the satellite structure, and on the top as well, where we do the experiments. And then we also have amateur radio PCB, 2 amateur radio experiments, which will also be showed later, and they are in the PCB on the very top. So this means InnoCube is assembled completely. Here you see an assembly view of the satellite. When we were assembling the structure, you can see all the inserted PCBs. You still see some wires. These are only the PCB, the electrical power connectors to the solar panels, and also for the antennas, the cable. So this means InnoCube is completed, but I have one more slide because we are aerospace information technology. It's not all about hardware. We also have software in the satellite, and I can announce that InnoCube proudly runs on Rhodos, even though I heard some, Rhodos is our main system. We developed it at the University of Würzburg, and other projects. I think from DLR was the beginning of this. What we also have built is in our working group is a software or framework which is called Corfu. Corfu is a configurable onboard software framework which provides the user to build software which runs on hardware based on apps and nodes. So we can build some specific apps which are doing some specific tasks, for example, which are handling telemetry, or which are handling telecommands, or which are handling ADCS algorithms, and they all can be put onto one node, onto one hardware node, and then we have a collection of apps running on different hardware nodes. For example, on the ADCS system, we have some general apps, the hardware monitor or the telecommand system, which runs on every app, on every node actually, and the ADCS system actually has some specific app which runs only on the ADCS system. So this Corfu framework actually makes it quite easy because it generates lots of code. It generates telecommands, telemetry on its own. It makes the software very robust because we are able to use pre-tested building blocks and just let the computer write code for us, which nowadays is very in. And but we have tested it before, and then we can use these building blocks to produce very robust software which does not have any copy and paste errors. So the structure on the satellite, as I said, we have the wireless SKITH bus. So we have the different nodes. We have the ADCS node, which I showed you, which was the box. We have the payload, 2 payload PCBs, the sun sensor, the OBC, the PCDU, and everything talks together over this wireless bus. It distributes its own health telemetry data. The comms node listens to all this traffic from the other nodes, collects everything, and then sends it down to the Earth via the transceiver. And the ground segment sends up telecommands. The transceiver actually is connected to the comms node. The comms node translates these messages and publishes them on the wireless bus. And every node which is on listens on the wireless bus and can take the telecommands which are for them and then are able to run these telecommands. Of course, we did some testing of the hardware and also of the reliability of the software. A common concern for wireless application in space is the problem with the thermal differences between different components, which might shift some frequencies and which in the end will cause some communication problems. We tested our complete satellite and also some development models inside a thermal vacuum chamber, and we were able to achieve more than 50 Kelvin difference in temperature, and we did not have any degradation of this wireless link. It did not, the wireless communication did not stop working after 50 degrees Kelvin. We just didn't have any more, any higher temperatures there. So it's very reliable in the expected temperature range, which we will have for components in space. We also did radiation testing. We did not have any degradation at 10 kilorats, which is more than the normal dose which we have about after 1 or 2 years in space. And we were still working at 37 kilorad, which was a high radiation dose test, which means, I actually don't recall, like 4 years of operation at least, where we did not have any problems with the wireless bus, and also all the other systems of the satellite. We also did some basic EMC testing. We did not have any interference with S-band transceivers, which are working in the same frequency range as the SKITH wireless bus at 2.4 gigahertz. And we did not have any interference actually with our UHF downlink, which was very important as well. So after I covered some software as well, now we can really say that the InnoCube is completed. I hope I gave you a brief overview of all the subsystems and the satellite itself. And now I hand over to Benjamin again.
Yeah, no, thank you, Tom. It was a very nice presentation. Can you go to Zoom? Mm-hmm. So yeah, thank you. And maybe also like we are about not like an hour away from the stream of the launch, like 40 or 50 minutes. We have some ground still to cover, but yeah, so we will watch in about 50 minutes the launch stream, and then see that we get InnoCube to space. And now Simon, my colleague, will tell you a bit more about the last payload, or not the last, one of the last payloads, the episode payload. Afterwards, we will have an overview of the AMSAT payload and the ground system and the launch later. So, Simon, the floor is yours. Thank you for joining us.
Thank you. Yeah, I'm Simon, and yeah, this is the episode payload. It's just a quick overview. Episode is an acronym for Experiment for Precise Orbit Determination. We are using a embedded hardware, which is really sophisticated small computer on the satellite to do a position determination in orbit. The payload is historically grown by student thesis. I've completed my master thesis in the payload, and many students have learned their way in embedded hardware and software inside this payload. With this software-defined radio-based orbit determination, we can also exploit the scientific usage of GNSS signals. For example, we have GNSS signals coming from around the Earth and also reflected from the Earth's surface. So we can analyze, for example, the sea level rise and also the atmospheric changes by propagating these signals through the atmosphere. So the payload itself is built on the lower side, on the zenith side of the satellite. It's composed of 3 parts. Firstly, we have the active payload inside the satellite, which is an embedded system containing 2 PCBs. One is mounted on the other. Then we have an aluminum heatsink and another heatsink which conducts the heat onto the structure of the satellite. And this is all on a module carrier board, which is plugged into the backplane of the satellite. Also, we have 2 GNSS antennas. One is an active antenna, where we have more gain, basically, and also we have a passive GNSS antenna. And we are covering the L1 band, which is around 1.6 gigahertz. And as mentioned before, we also have this laser retroreflector, which is based on a design of a previous mission of DLR. It's on the other side, basically, of the satellite, which is nadir pointing. There are 4 prisms of around 8 millimeters, and these are trackable by the ground station, for example. On the software itself, on the small computer, we are using a program called GNSS SDR. This is an open source software project from ESA, developed in Spain. We can use SDRs on ground to basically calculate our position already, to use standard hardware, but on the satellite we are using specialized hardware and also use specialized software on the payload as well. This system, the software is GNU Radio based. We'll come also back to GNU Radio later, what this is. And in this software we have the flexibility we need to operate a GNSS receiver in orbit. This is, for example, with the high velocity our satellite has and the high Doppler shift the signal experiences. So the goals for the payload, well, firstly, it's an operational payload. We want to demonstrate position determination also with students and also educate them further in operating a satellite. Also, we want to use the improved the positions for improved orbit predictions, so we can propagate our own orbit and say much more accurately how the position of the satellite is. And also we use this opportunity to do a payload verification to enhance the payload for possible future missions, which are unfortunately not funded yet. But techniques and scientific uses like GNSS reflectometry, where you use reflected signals from the Earth's surface, are possible on a CubeSat, and also GNSS radio occultation, where you look at the bending of the signal through the atmosphere and then measure the atmospheric changes. It's also possible as well as multiband GNSS, which can be operated then. Right, and we also have this laser retroreflector, which is coming in very nicely with our new TU Berlin optical ground station, which is currently in construction. We expect it to be operational soon in the next months. Yeah, then we can also track our satellite with satellite laser ranging. So we send a pulse from the ground station to the satellite and get some photons back. And with multiple measurements, we can also propagate our orbit more precisely afterwards, I think. And with this, I will go to the...
Yeah, thank you, Simon. The next part is our last payloads, our amateur payloads, which our friends and colleagues from the amateur club and from the institute actually does. So thank you for joining us, and you have the floor.
Yes, as you've already heard, we also have an amateur radio payload on the satellite. So for those who might not be aware, amateur radio is an internationally recognized radio service. So there are radio amateurs all over the world, and they have dedicated frequencies which are used for training themselves in the art of radio operations and developing radio technologies. They can be used to intercommunicate between the radio amateurs, and they can also be used to investigate new technologies for radio communication. And importantly for us, they can also be used to communicate into space. The limits on amateur radio is, of course, that it's defined to be an amateur thing. So amateur doesn't mean that you're doing it badly. It just means that you're doing it with a personal aim and not with any commercial interest behind it. And for this, you get dedicated frequency bands, which you have to share with the other radio amateurs, of course. And you can use relatively high powers to do your operation and design and build your own hardware, which is very difficult to do otherwise. At TU Berlin, we have a proud history of amateur radio, going back to the early days of radio communication existing at all on Earth. So we have an amateur radio club called AFUTUB, which is an open hackspace for radio enthusiasts, where we meet and discuss, and we also have built our own amateur radio station at the rooftop of the TU Berlin main building. And then we also have a lot of teaching offerings related to amateur radio. So there's the Sierra project, which is an interdisciplinary teaching cooperation between the amateur radio group, as well as the chair of space technology, where we are right now, and the chair of high frequency technology. And the courses we offer include the amateur radio course, where students can prepare themselves with our help for the exam that they'll have to take to participate in the amateur radio, as well as 2 projects related to satellite communication and radio astronomy, where students get certain work packages which they investigate on their own and do some engineering or scientific work related to the topics. And in the satellite communication project of last semester, we also had one work package where the students investigated the amateur radio payload in InnoCube. Originally it was supposed to be delivered by another radio amateur, but unfortunately he had to drop out, and that gave us the opportunity to jump in and use the free slot for our own purposes. Yeah, so what is the goal? We want, we had a relatively short timeline, so the payload isn't going to do anything that wasn't seen before, but we wanted still to have something on the satellite that would be interesting to radio amateurs. So the payload is capable of sending out CW beacons, so this is Morse code beacons that are relatively easy to receive and decode for radio amateurs, as well as slow scan television images. So it's a fairly old and reliable way to transmit images. Despite having television in the name, it's not a video, it's just a single image every 90 seconds or so. Yeah, and to develop the hardware in time, we had to go with a very simple architecture. So we have a pre-made transceiver, of course a microcontroller to control it, some flash storage to store our image data that we want to send, as well as a temperature sensor. Yeah. To develop the hardware, we used a little hexagonal development board, which you can also see on the slides here. And here you can see where the microcontroller, transceiver, flash, storage, and temperature sensor were. And then when we look at the actual flight hardware, of course, all the same components are here. You can see the temperature sensor, unfortunately, because it's covered by another payload that we'll talk about shortly. But you can see the transceiver here, the flash storage and the MCU, as well as, of course, the SKITH module that we need to communicate from our payload to the rest of the satellite, which you've already heard a lot about. Yeah. Our payload, of course, also needs software, and that software was written in C++, while our students laid the groundwork to enable the operation of the amateur payload. They didn't get around to finish their work in time, so yeah, Martin and I, who are working here at the chair, as well as being involved in the amateur radio group, we had a bit of a quick coding session and took about a month to write the actual flight software. And it's capable of, as I said, sending out Morse beacons as well as SSTV images. And it can also automatically alternate between both, so that you can first tell the satellite is there by the relatively easy to receive Morse code, and then be prepared to receive the image that's coming afterwards. The payload also has a firmware update capability, so we can also add new features later, as well as, of course, being able to be remotely controlled, so we can tell it to send specific images. Yeah, and the control can be done either directly by communicating with the payload through its own frequency shift keying uplink, or via the SKITH module by communicating with the satellite bus. Yeah, and then Sebastian is going to tell you more about the other payload.
Hello, I'm Sebastian, Delta Lima 7 Bravo Sierra Tango. I'm also radio amateur, but just as a disclaimer, I'm going to talk not about amateur radio. So we're part of the amateur radio payload because we're physically connected to the amateur radio payload, but the frequency band, which Tim already showed here, for those who are not German speakers, it's like nice here, but did you ever spend time on 401.5 megahertz? This is not an amateur radio band, so what are we doing there on this band? I'm talking about SIDLog and the beacon experiment, which is connected to SIDLog. We are like concerned about all the space objects up there. So today or nowadays we have exponentially increasing number of objects. So depending on the projections in the coming decades, we have tens of thousands to millions objects there. And we have right now mainly stochastic orbital traffic management, which means we're having a starting object, an injecting object, where the rocket is going to deploy or the dispenser is going to deploy the satellite. And then we have our drag from the atmospheric drag or from the drag from the sun or whatever. And then we're decreasing the orbit until we burn in the atmosphere. There are some concepts of using engines or solar sails or whatever, but the main topic here is to have an overview over all the orbiting objects. Right now we have no interoperable passive tracking system. What can we do? We can detect objects and we need to identify them afterwards. And first, the most oldest thing is to use basic telescopes, so just use the reflection of the satellites. So everyone knows probably the iridium flares or the ISS, or nowadays it's mostly the SpaceX, the starting satellites, where you can see the illuminating chain on the heavens. So you use telescopes or your eyes on that. You can use radar reflections, or you can even use laser reflections. So for lasers, you need to have a clue roughly where is my object roundabout, and then you need to do some kind of detective work. So what is actually my object? So we know there is an object, it's a small object, it's a big object, it's whatever. So you need to analyze the characteristics of the reflections or the radio transmissions, or you need to check the separation parameters, meaning, okay, object number 5 is supposed to be me. And what is the challenge? It's to date, it's manual work, so it's really handwork. So you need to analyze the data. Somebody has to make up his mind or her mind about this object. Could it be my satellite? And this is a process which is very difficult to automate. So today the identification takes days, months, or even forever. So sometimes till today we have no idea which satellite is exactly which satellite. And as well, we have limited tracking capabilities and capacities of radar system. So we're trying to close the gap here. And we have different tracking aids, we call them. So we can use optical aids or radio aids. And we can distinguish them in passive and active tracking aids. And we analyzed all of them. I don't want to go too much into detail, but there's a good combination about autonomous encoded radio sources, like we do in our projects, and I'm going to explain very soon. And passive solutions, like we've already heard about the CCRs, corner cube reflectors, or even high albedo surfaces or whatever, to have accurate positioning information about the satellites. So the radio signal for the rough estimate, and the optical tracking aid to have an accurate positioning in the end. What is the motivation? We want to close the gap to radar systems, speaking of trackability, because we can also track smaller objects, because to date it's difficult, for example, for a pocket cube, which is like 1/8 of a 1 unit satellite. So they are really hard to find, so we can make them trackable. We can add information, additional information to the signal. So what is my identification? So that would be the first thing. And then, for example, also status information, like if the satellite is still operated, do I have a working engine or not? What is the health state of the satellite, and whatever. Scalability. So if we compare it to the real world role models, we also have for maritime traffic or for air traffic management, we also have broadcast systems. We have radar systems as well, but we have broadcast systems to make a quick acquisition of the object and of the signal. But today we have nothing for the outer space. The features offered in the future could be facilitating first contact information to re-entry, simplify emergency intervention, which is an optional thing, so which is not the main focus right now. So because we're focusing on the orbit determination and the identification, but with an uplink channel, you can also have a redundant channel to eject a re-entry mechanism or trigger reboot or whatever. This is mainly for sustainability aspects, so economic sustainability, because our space assets out there are worth very much typically, so we put much work and much money into that. And also from the ecological perspective, because the outer space or the orbits are also a very useful resource for the future, and we don't want to pollute them. So the first of its kind was the SIDLOC experiment. This is done by the Libre Space Foundation based in Greece. They have a manifesto with 5 principles and 4 pillars of open knowledge. And they're funded mainly with ESA projects and with their free and open source community projects. So lots of volunteers are also working on that. And their most famous project is the SATNOX, the Open Ground Station Network, which you might know. The scope of SIDLOC is identification and tracking via Doppler shift measurements. And they propose coexistence with other space operations with spread spectrum. And the project state right now, you can check on 2 different talks. So there's from last year, so around about 1 year ago, FOSDEM talk in Brussels. And just recently on the 38C3 in Hamburg, which is the Chaos Communication Congress, there was a talk especially about the Ariane 6 experiment, because on the upper stage of the Ariane 6 was a SIDLOC in a shape of a pocket cube, which is the 5 by 5 by 5. So this is the result. I don't want to go too much into the details, but the principle actually worked on the Ariane 6 upper stage. The battery was just powered for a few hours because the Ariane 6 upper stage was supposed to orbit just 2 times and then re-enter. We know it didn't happen. And what is our... Oh, this rotation is nice. And we're currently working towards a European cooperation, especially with SIDLOC and international solution, looking into regulatory frameworks, want to miniaturize everything. I love this Earth, it's very nice. And our vision would be a simple plug-and-play attachment and no expensive and time-consuming frequency coordination in the future. Whoop. Okay, this is our launch schedule for the SIDLOC and the beacon experiments, which are scheduled as of today. So maybe in the future there's more upcoming, but from TU Berlin there's the InnoCube today, hopefully. And at the end of 2026, the Queen, which is a 50-kilogram satellite from TU Berlin. And I'm going to hand over to Felix, with some technical details.
So hi, I'm Felix. I'm part of the technical staff of Beacon. And as you already can see here, this is the actual flight hardware we integrated for InnoCube. And this consists basically of once the amateur radio payload, which the amateur radio club and some students have provided, which is connected to the main antenna of the InnoCube satellite, and also our beacon or SIDLOC experiment, which is also connected to the SKITH path and has its own dedicated 401 megahertz antenna. So we inherited this design from the Libre Space Foundation, so we basically adopted their design for this opportunity, because as we already mentioned, this was a short notice opportunity to fill this gap in the satellite. So we're talking about 2 months from first idea, we order the parts, to we have to deliver the flight model. So that's the reason why we copied a lot from LibreSpace there. So they have a really powerful setup there, basically a software-defined radio transceiver there, which is a really excellent platform for experimentation. But if you're talking about trackability and longevity of space hardware, then that's probably not the best hardware. So that's the reason why we in future, now in the Beacon project, that's also why it's mentioned about Beacon, we want to minimize our system in a patch, so 50 by 50 by 6 millimeters, so which can easily be attached to an outside of a CubeSat there, and build this in a discrete manner, so we don't have some kind of vendor lock or higher failure rates due to radiation. So that's all around the Beacon project there. So we really want to do an energy autonomous system there, which is almost bulletproof, and be able to provide a solution which then can be used to track multiple satellites. So then I would hand back to Benny.
Thank you. And yeah, so we have a small update also on the launch. It's slightly shifted back for 20 minutes. We have 20 minutes more to entertain you here. So we can pull out our surprise probably for you. And we heard about now all the satellite system, all the technology, but one thing we are missing is actually what happens on ground. So now I will hand over again to Simon, and he will give you a quick overview what our setup here on ground is, and also then what we will expect from the launch, how the launch will be performed, and what our next step in the first contact are. Thank you, Simon.
Right. Now for the interesting stuff. What are we doing today, and what's going to happen? So firstly, as we talked before, we are using UHF ham radio in our satellite, which is in a frequency of 435 to 438 megahertz. We are nearly in the middle of it at 435.95. And you could also receive us there if you had a little stick like this, for example. To give it a bit of context, FM radio would be usually in the range of 100 megahertz. So we're just a bit above that. So for low Earth orbit satellites, which are really close to the Earth, like 400 to 600 kilometers, UHF radio is still primarily used for commanding small satellites. If you look closely to the launch of Transporter 12, most of them are using UHF communication either in the ham radio band or also in the commercial band of 401 megahertz. We have a lot of challenges compared to radio communications on Earth. We have the satellite, which is traveling at a fantastic speed of around 7 kilometers per second or 28,000 kilometers an hour. So we have a very high range rate, and the satellite is also pretty far away. We are expecting to be launched at around 520 kilometers. So the least distance we have to our satellite is 500 kilometers. But usually the passes are not straight over the ground station, so it's a bit askew. So the range we are operating in ranges from around 2,000 kilometers to, in the best case, 500 kilometers. So at InnoCube, we don't stop at the bus, we don't stop at the batteries. we also have an innovative ground station. We are the first, at least the first TU Berlin satellite, which is operating the satellite with software-defined radio. Of course, we already heard the satellites with software-defined radios, but we will be the first mission to command satellites actually with SDRs on a regular basis. So for the ground station, we are starting with our satellite. This is in orbit, and it flies around, whether we are tracking it or not. It just flies without us ever doing anything. Then we have our ground station. This is actually on the roof ahead of us, on the 6th floor, like 74 meters above sea level. And yeah, this is the point where we are communication with. A bit more insight. We have this wireless bus, and for the wireless bus to communicate the messages which are going around on the bus, we still are using a transceiver, which is mentioned by Tom before, which transmits the telemetry to our ground station here, and we are also commanding the satellite, of course, from the ground. Right, and we are using an SDR instead of a classic radio transceiver. Right, this is a very short overview how this looks. It's a fairly simple setup. On the ground station, we have a PC, we have a server, which we are also operating on later today. On this laptop, actually, we have the SDR, which is connected with an USB cable, and to the SDR we have a power amplifier connected, which is then connected to the actual antenna. In this loop, there's also a cavity filter, bandpass. This is because in Berlin or everywhere in the world, the UHF band is quite noisy, and we have a lot of communication which is around this band, and to have a clear signal, we are using this cavity filter, which blocks out all signals outside of the band we are targeting in. So our signal is around 6 kilohertz in width, and for the cavity filter, this filter has about a width of 200 kilohertz, and everything outside of this band we don't even hear. And then we also have a low noise amplifier behind it, which delivers us 20 dB additional gain. So this amplifies the signal around by a factor of, I think, 1000. Right. This ground station, well, it was there, but it was not used often. The setup was not great. We had to service it, and for this, my colleagues, which are luckily not afraid of heights, were in September. We started first maintaining the antenna. This is Benjamin up on the ladder and Tristan. And however, it didn't stop there. As small satellite missions or any project goes, sometimes you have to work until the last minute. This was in September, and this picture is from last Friday. This was the last time we still had to go on the roof and check some things on the antenna, but afterwards we tested it, and now it's ready. It's ready when the satellite comes. Right, now I've talked a bit before about GNU Radio. GNU Radio is basically a program. It's a programming language to use signal processing with an SDR. So this can be either this little stick, this little RTL SDR stick, as you call it, where you can, for example, watch television with terrestrial television, and also like basic things like FM radio. You have these small coding blocks here. Every code block does a discrete function. For classical transceivers, you would either use a separate component like a ADC, like an analog digital converter, or maybe a filter, something like that. But these are mostly hardware components. With an SDR, we can just use software to do these functions. Right, and as it turns out, you can also operate satellites with it. The main advantage of it is we are very flexible. Every satellite which is on the rocket later on, with this SDR, we would be able to encode it. We can change the protocol, we can change the modulation, we can change every aspect of the signal we are receiving, and receive and decode every signal we get. Another advantage is we can also change the parameters in real time during the passes. This would not be the protocol or modulation, but small parameters like the gain, for example, depending on the situation. If we have a low noise situation, if we have high noise, we could change all that live during a pass. So now I've talked a bit about the passes. How does this look like? So there's this object flying towards us, but yeah, maybe we should just watch a video. Could you start the video maybe? So here this is InnoCube. This is the ground track, which we will see later on, and it flies around the Earth. The Earth is moving around it, and yeah, it flew away and then it's gone. And now it comes again. Oh, now we are in contact. Here's Berlin somewhere, and then we can operate it. So we have just this small window. It's around 10 minutes for our orbit, and maybe you can do it again. So now it comes, now we are in range, and then it's gone again. So we have a high pressure situation in that moment. We have the satellite, in this case, coming from south, going north, and it flies around, a bit askew from our ground station, and we have to track it. We have to arrange the speed, and yeah, all that has to be done in the 10-11 minutes in the pass. So maybe I can, yeah. So what we just saw is, firstly, it was this pass. So the satellite comes around here at 2131, and then it goes up here. So this is an azimuth. This is a polar plot. So we are basically in the middle, and if you have a map, north, south, east, west laid out flat before you, you would have the satellite flying basically overhead in these directions, and the elevation it has above the horizon would be here. So it starts fairly low, and then it goes higher up to an elevation of about 35 degrees, and then it goes down again until we lose it behind the horizon as well. And as I said, the satellite is at a very high velocity, so the signal is Doppler shifted. So the signal has a shift by because of its high velocity, and we have to account for that. In both cases, when we want to transmit to the satellite, and also on the other side if we want to receive signals from it. Right, and this is very, it's not highly complex, but it is tedious. And our ground station, which is basically, this is a view of GNU Radio. It does all that. It controls the Doppler shift for transmitting and receiving. It tracks it around the relative velocity of the satellite. For example, at first it comes at a high velocity, then when it's directly above us, the relative velocity is 0, and then it flies off. So it's like a shift coming from around minus 10 kilohertz and going through 0 and then plus 10 kilohertz. And this all has to be done in software as well. Additionally, we have our antenna, and also we have to point the antenna to the satellite. It's a high gain, high directional antenna, so it has to point accordingly where the satellite is. And the antenna on the roof has this rotor, so we can move it 360 degrees and also 90 degree upwards. And this also has to be automatically done in the path. Also, here we have the control panel. We can do things like adjust the offset of the frequency, and also the gain of the software gain of the SDR. We will do that live in real time, depending what we are seeing. And we will also see this waterfall diagram. So this is basically coming. You see the signal in time going down, and we will see what's going on there. And this is actually during a pass we did in October from a different satellite. This one. This is one pretty similar to our satellite, and just to test that we are ready, we used satellites which are not ours but known to transmit telemetry over Berlin, and used them to decode them, basically. That's what we did, and this is what this panel is. And this was all working pretty good. Right. Now, we also did that for our own satellite. We have to, before it's launched into orbit, we have to check with the SDR, if we send a signal, it should also receive it. And this is what we did. And it can be seen in this video. This is an antenna deployment test. So what we will see, after launch, it shall deploy the antenna rods, and you should see this here, around there. So basically at the top of the satellite you should see it, and maybe you can play it. Now it should go. Right, there's the first door behind there. This is the second door. The third door is here. And the last one took a bit of time, but it also deployed. And then after the antenna is deployed, because before the antenna is deployed we couldn't operate it, but this is an automation. But after that we could also speak in both directions with the satellite. Right, now we've seen if the satellite comes, we are ready. So now we're waiting for launch. This ominous launch, what's that? Right, we are watching the Transporter 12 mission now. It says here start around 1849 UTC. We've just heard it's about 20 minutes delayed already, but yeah. This is basically this rocket, which has flown already in November on N-roll 126. It's a reused booster. This rocket will bring, this is the Falcon 9 rocket, if you are not aware. It will bring 131 payloads into orbit. So 131 missions like ourselves will be getting into orbit, and will have their mission started just like we are. notably, no Starlink missions, no Starlink satellites are on the rocket, and all satellites are small sat rideshare satellites. So they are all fairly small. Some are obviously bigger than others, but all of them are generally known as small satellites. We are launched into a sun-synchronous orbit with an altitude of around 520 kilometers. This means the orbit follows the path of the sun. So every pass, every time the satellite flies over a point of the Earth, the local time which it flies over has basically the same time. And as I've said already, it's a reused booster. Right, to go into more detail, I will not do everything, but what the rocket does is basically it's launched, it starts its ascent, it's not going straight up, it goes a bit to the side. Then there's a stage separation, so once the first stage is nearly completely burned out, the stages are separated. The first stage will be flipped and perform a boost back burn, and then do this vertical landing later. But we are looking at the second stage. We will have a fairing separation once it is in space. There's no air, so we don't need this fairing. And then around, an hour after launch, we will have payload separation. So after an hour, every one of these 131 payloads will be deployed in a controlled sequence. And we are anxiously awaiting that moment. And yes, now this is for the whole rocket, but for us, these times are not correct now because the launch is delayed as this happens in space and in railway traffic as well. So the launch is delayed 20 minutes. So the orbit insertion, basically where the separation of InnoCube happens, is around shortly after 8 UTC, which is 9 o'clock, shortly after 9 o'clock local time in Berlin. Then the satellite flies around and it starts its antenna deployment approximately 31 minutes after it's inserted out of the rocket. Then these 4 rods are deploying out, and then another 90 minutes approximately at 10:30 local time, now probably 10:50 local time. We will be ready here for the satellite, and we will be sending our telecommands for it starting its operation in orbit. Then we have 10 minutes, a bit more than 10 minutes for the first pass, and then we will see if it answers us back. Yes, and then we have the second AOS, which is about 1.5 hours later, but this is a very, very low elevation pass, and we will see whether we will be operating this at all. Right. So this is what we are gonna expect the rest of the evening, and with this I will go back to Benjamin.
Yeah, thank you. So, so the live stream will start in, what time is it actually right now? 6:30, so in 20 minutes. So actually we were right in time with our program. we are quite proud of it, because the stream should have started now with the original schedule. But okay, now we have 20 minutes, and I thought you we have a surprise. So we have prepared a small quiz for you. How are we gonna do it now? And you can also, I think, win something, but I only heard of that we have this surprise for you, and Simon is again preparing this, but what is our director? Are we ready for our quiz? In a couple of seconds. So I hope you enjoyed so far this event. I liked it quite well, and I'm pretty excited for the launch. So 20 minutes. So yeah, so what we will do now, we will do our quiz, then depending how long it goes, we will then just wait that the the stream starts, and we will tune in to the live stream of the SpaceX and probably give some moderation if they don't do, but basically enjoying the launch. And then at some point when the second stage or cutoff is, there is this time between the separation. We will just observe it, have a small break, and then enter when the payload separation is again in our live stream event, and finish up afterwards. Or basically you can watch us silently still doing our contact here, but we won't moderate anything or talking to you anymore. Maybe after the contact we can give a feedback how it was, but that's then later on today. So, are we ready for our quiz? I hope you didn't fall asleep. And now I will give to Simon.
Yes, one moment. Nearly ready. Ich kann das hier nicht rüberschieben. Hm? Mach mal bitte. Naja, der YouTube-Stream.
Ja? Ach so.
Hm? Das?
Ja, das ist aber wieder klar.
Also. Wo ist der Presenter? Ach so, na gut. Right, here's the link. So we have a small quiz which is covering some scientific questions from our mission and some not so scientific questions. And this is on quizzes. Thanks again for Victoria to prepare the quiz. And you can join the quiz by either joinmyquiz.com and entering the code, or you can just scan the QR code. So maybe we can say we give each participant maybe 1.5 minutes to join, and then we can start the quiz. And as already mentioned, we have also prizes. Where do we have them? So you can win this InnoCube mug. Can you see that? This InnoCube mug, I will get it out, hopefully not break it. This is the mug with the logo on it. And we also have some stickers we will also put as prize as well. Right. Maybe 20 more seconds to join. Okay, we have a lot of competition now. Okay, then 5 seconds, and I guess we start now. Right. Did we start? Okay. First, I will not read the question, or I will read the question, but you can already answer it if you read it. Okay, apparently I cannot see the question, so you have to answer it yourselves. Wo denn? Okay. Right, what was the boot counter of the InnoCube flight model before integration? 169, 101, or 420? So maybe as a side note, if you are a satellite engineer or you are into aeronautics, you do not have an advantage today. So, next question, I guess. One moment. Right, it was actually 69. But by coincidence. Right, the next question is how many circuit boards does InnoCube have in total? So 7, 5, 32, or 69? Who knows? Right, I guess we are done. We counted it actually a few weeks ago because we didn't really have an oversight how many there actually were, but it is 32 PCBs on it. Some are small, some are big. The biggest one is the backplane and the solar panels, but yeah, it's 32 PCBs. Right, next question. Right. How many business trips did I do to Würzburg? Yeah. 0, 7, 14, or 30? Yeah. Very interesting. Well, it was already, yeah, it's 14 business trips. So 14 times I had to go to visit Tom and the team in Würzburg. Right, next questions. Next question. How many power cables or how many wires does InnoCube actually have? 0, 1 to 100, 100 to 200, or we don't actually know? Kann ich das sagen? Kann ich das sagen? Wie viele es waren? Right, it was actually 168 wires. So most of them are power cables, like ground and plus. but we also have the coaxial cables to the antennas, to the transceivers, and yeah, but no data was transferred over the cables. Right, next question. How many kilometers has InnoCube driven on the freeway or autobahn? 0, 69, 420, or 1,234? Also a very scientific question. Yeah, actually it only traveled by Deutsche Bahn. Psst. Okay, next question. How many different means of transportation has InnoCube already used? So for this question, we are also including the one it will use in the next, depending on the delay, in the next hour or in the next days. Right, the answer is 6. It traveled by plane, by rocket, and then it also was in the U-Bahn, in the car between Exolaunch and the testing facilities, and some more. In the Deutsche Bahn, and the last one I don't know yet. What? Regio, probably, yeah. We didn't ride it on the bicycle, yeah. Yeah, we carried it as well, so maybe it's 7, but we didn't count that. How many students were involved in the project? So we have a high emphasis on students. The E in InnoCube stands for education. So yeah, a very important aspect of the project, actually. Yeah, it was 57 students. Most of them were writing their bachelor or master thesis, but we also had a lot of internships which are required in Würzburg as part of the education there. Right, I'm a cycling enthusiast, so the question is, are there bicycle parts installed on InnoCube? So yeah, maybe only I know. Yeah, the answer is actually yes. The shifting wires from bicycles make a pretty good antenna. For amateur radio. Right. What is the InnoCube working lunch? For our business trips, we had a traditional lunch we always did, so you might guess that. Yeah, it was actually burritos. Thanks mostly to Tristan, who's a pretty good cook outside of embedded software. Right. Which framework is used on InnoCube? Corfu, Mykonos, Crete, or Rhodos? I don't see it. Maybe this is a trick question. Yeah, it's probably a trick question because Corfu is basically Rhodos for InnoCube, for wireless framework. Very important question. What are the names of the team's dogs? The most important members of the mission. Yeah, maybe you can see them here as well. Yeah. Very Toby at the top. So now we have the last question, which decides who gets the InnoCube mark. Very important last question. Which subsystem of a satellite is the most important? Payload, communication, electrical power supply, or is there actually none? Right. The answer is actually, if you've heard the satellite technology course of TU Berlin, you might have guessed it. There's actually no most important subsystem. Everyone is created equal. Right, that's it. And now, do we have results? I guess Toby won. Which one? Do you know? Okay, so maybe the Toby M has won. Maybe we can organize more mugs for every Toby, I guess. But yeah, thanks for participating. We will reach out to the winning Toby, and with this, I guess I go back to Benjamin.
Genau, you can reach out to us actually.
Oh.
Soweit. Yeah, you can reach out to us. Also, I think, I don't know, the winning Toby maybe to us that we can get you somewhere how the price. And if you have any questions, Tom and me are very happy to answer them. You can reach us via mail, or we will forward it to the people who can answer them. And now I think it's about time that our stream will start, hopefully. I didn't have any info of further delays yet. I hope, yeah, you are still there. You liked it a little bit. And we will now try to connect to the live stream. Ja, kann man bestimmt. Gleich. Sieht gut aus. Da sind wir bei T-10. Genau so, wie es sein soll. Oh, sorry. In English, yeah. T-10 and the stream is starting. So I think we will wait a little bit, look a bit into it, and then I will find a co-moderator and we will see that we can start the launch. So now we will just keep listening to the stream of the SpaceX for a while.
We are currently working towards a liftoff of 11:09 a.m. Pacific time, which is in about 10 minutes from now. If needed, there is a backup launch opportunity tomorrow, January 15th, at the same time. But right now, the weather is currently green on the Central Coast, and the range is ready to support. With that, let's take a look at one of the payloads launching on today's mission, MBZ-SAT. Developed entirely by UAE engineers at the Mohammed bin Rashid Space Center, or MBRSC, the MBZ-SAT Earth Observation Satellite will become the most advanced satellite in the region, offering unprecedented image accuracy and offer improved data transfer and download speeds. Here's more from our customer, MBRSC.
It's our biggest satellite that we've ever built. It's about 1-ton system, producing very high quality resolution data that will benefit a lot of entities locally and globally. But the key factor here is that this satellite is fully designed, integrated, assembled, all of the software, everything is done here at the Mohammed bin Rashid Space Center.
You can imagine from 500 kilometers you can image a square. That gives you the ability to put these pixels back with each other to create an image. And that image will give you the ability to extract information.
It's very exciting to work with a team that is full of experts who have gained knowledge from different projects all over space. So it's really exciting to work with the team.
The Falcon 9 rocket supporting today's mission is a two-stage rocket designed for reliable and safe transport of satellites, cargo, and people. At the very top of the rocket is the payload fairing. The fairing is a protective shell that houses all the payloads, shielding them from the aerodynamic heating until the vehicle is outside of the Earth's atmosphere. The aerodynamic shape of the fairing also contributes to Falcon 9's overall efficiency, helping to reduce drag while the vehicle accelerates through the atmosphere. Once in space, the two fairing halves separate and fall back to Earth, where they will be recovered by one of our recovery vessels to be refurbished and reused on future flights. Both halves of this fairing are flight-proven, with one side flying for its 19th time today and the other for its 18th time. And inside those fairings is today's payload stack, which was encapsulated just a few days ago, and this is actually our tallest stack to date.
Engine chill has started.
Right below the fairing, we have our second stage, which houses our single Merlin vacuum engine, or MVAC, which will take our payloads to their drop-off point. Below the second stage is the black carbon fiber inner stage, where the MVAC engine is located. The inner stage connects the two stages and houses a center pusher that allows the first and second stage to separate during flight. Below that, we have the first stage, which we usually refer to as the booster. The first stage makes up the bottom 2/3 of the vehicle and has 9 Merlin M1D engines at the bottom. Those 9 Merlin engines generate more than 1.7 million pounds of thrust.
Stage 1, RP1 load is complete.
The first stage supporting today's mission will be marking its second flight today, having previously flown the NROL 126 mission. At about 2.5 minutes into flight, the first stage will separate and make its way back to Earth and attempt a land landing at LZ4, which you see right there on your screen, which isn't too far from the launch pad. If successful, this will be the 397th landing of an orbital class rocket. Because this is a return to launch site landing, during re-entry, when the booster slows down from supersonic speeds, people in the immediate area may hear a brief double clap of a thunder-like sound referred to as a sonic boom. Reusability is the key to our future in space, and the sonic booms created by returning boosters are unique to reusable vehicles. Similar sonic booms were heard during the return and landing of NASA's space shuttle and famously occur following a Falcon Heavy launch when 2 side boosters return at the same time to the launch site at Cape Canaveral, creating a unique double sonic boom. While these have become well known to rocket enthusiasts at the Cape, they're becoming more well known on the Central Coast and Texas, where our Starship vehicle's Super Heavy booster returns to the launch tower. To get an idea of how this looks and sounds, here's a look at what some of these booster returns have looked and sounded like on a few previous missions.
I know a lot of people will be excited when they hear the sonic boom.
And these are going to provide quite a show because you're going to hear those sonic booms.
Sonic boom. Booster landing leg deployed.
That sonic boom is great for us.
That thunderclap broke the sound barrier.
Side booster separation confirmed.
Just heard the 2 sonic booms here in the room.
Booster landing confirmed.
At just under T-4 minutes, all systems are currently go for an on-time liftoff. Next up, the truss structure next to the vehicle, known as a strongback, will start to retract. In preparation for retraction, the clamps around the second stage will open, which, if we look on our screen, they have already opened. And then the strongback will recline away from the vehicle, which you can see it is slowly moving away. In addition to helping drive down the cost of access to space by flying reusable vehicles, SpaceX's dedicated rideshare flights to sun-synchronous orbit provide small satellite operators competitive pricing, increased flight opportunities, and flexibility. As the demand for rideshare missions continues to rise, our rideshare program was expanded to accommodate even more smallsats looking for rides to orbit. Falcon 9 launched its second bandwagon mission last year, Bandwagon 2, a separate line of rideshare missions to deliver spacecraft to mid-inclination orbit rather than to transporters sun-synchronous orbit. Mid-inclined orbits are appealing to a growing number of customers, especially to remote sensing companies that want to strengthen their coverage over areas like parts of Asia and the Middle East. Rideshare significantly increases access to space for small satellite operators around the world, and we're excited to be able to offer these launch opportunities for our customers. For more information on these and opportunities to other orbits, visit spacex.com/launches. So at T-minus 3 minutes, we had LOX load completion on the first stage, and we're coming up on LOX load completion on the second stage in just under 15 seconds from now.
Stage 2 LOX load is complete.
Great call out there, telling us that Falcon 9 is now fully loaded with propellant. Coming up around at T-minus 1 minute, Falcon 9 will be in startup, which is when the internal flight computers will have taken over.
Ground gas closeouts.
That white cloud is venting from the TE LOX line, which is completely normal.
Okay, jetzt ist es gleich soweit. Wir sind hier. Also in English, sorry. Yeah, now it's about time. You see, I'm nervous already. So yeah, it's about time. We are waiting
Falcon 9 is
to
in
send
startup.
InnoCube into space. So fingers crossed and good luck. Good journey, InnoCube. Bon voyage.
Good luck. Launch director, go for launch.
We just heard from the launch director, so at T-minus 40 seconds, all systems are go for launch of Transporter 12.
T-minus 30 seconds. T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff of the Falcon 9. Go SpaceX. Go Transporter 12.
Vehicle is pitching downrange.
Stage 1 propulsion is nominal.
We are now 32 seconds into flight. Falcon 9 has cleared the tower at Space Launch Complex 4 East, and we're currently throttling down to prepare for max Q, which is the point of maximum aerodynamic stress on the vehicle.
Power and telemetry nominal.
Falcon 9 is supersonic. Max Q.
We just had max Q. Now we have 5 events coming up in quick succession, starting with MECO, then stage separation, stage 1 flip, second engine start or SES1, and the start of boost backburn.
MVAC shell has started.
MECO is main engine cutoff when all 9 M1Ds on the first stage shut down. Stage separation is when the first and second stage separate from one another. Stage 1 flip is when the booster flips 180 degrees. Second engine start is when the MVAC engine on the second stage will light for its first time. And boost backburn is used to arrest the forward velocity and return the first stage back towards the landing site. So all of those coming up in a few seconds. Watch out for them.
Main engine cutoff.
Stage separation confirmed.
MVAC ignition.
Stage 1 boost back startup.
And there you heard, and we had some awesome views of those 5 events that happened back to back, which were main engine cutoff, stage separation, stage 1 flip, second engine start 1, and boost back burn on the first stage. Coming up next will be fairing separation.
Fairing separation confirmed.
Great call out there of fairing separation and an awesome view of our payloads. As a reminder, those fairings will make their way back to Earth for recovery. Both halves of the fairing are flight proven, with one side flying for its 19th time and the other for its 18th time.
Stage 1 boost back shut down.
And we just had the end of boost back burn. The next major milestone coming up is entry burn on our first stage, which is scheduled to occur around the T+6 minute mark.
Vehicles are on a nominal trajectory.
On the left-hand side of your screen, we just saw the 4 grid fins deploy. Falcon 9 is equipped with 4 hypersonic grid fins positioned near the top of the first stage that help steer the first stage as it returns to Earth. And we're currently in our first MVAC burn, and this burn should last for another few minutes. And as I mentioned, the next milestone will be the first stage entry burn, which is coming up in about a minute and a half. Today, Falcon 9 is performing 2 burns in order to land. That first burn, known as the entry burn, slows the vehicle down before hitting the denser parts of the Earth's atmosphere. Today's entry burn will be a single-engine entry burn where only E9 will relight. Without this burn, we'd only be using the atmospheric drag to slow down Falcon 9, which would add extra stress to the vehicle. Following entry burn, the booster will initiate the landing burn, which should slow down the vehicle even more for a successful landing. The white puffs coming off of Falcon 9 that you see on your screen are cold nitrogen gas, which help with attitude control. An awesome view of the Channel Islands on the right-hand side of your screen, coming up on the start of entry burn in just a few seconds.
Stage 1 entry burn startup.
There's the start of entry burn. It should last about 15 seconds.
Stage 1 entry burn shutdown.
And we just had confirmation of entry burn shutdown. And as I mentioned earlier, we will be attempting to recover this booster for the second time today and are targeting a landing
Stage 1 FTS has safed
at Vandenberg's LZ4. Today's landing burn attempt will be a 3-engine landing burn where engines 1, 5, and 9 will relight to really quickly slow down the vehicle before touching down.
Stage 1 transonic. Stage 1 landing burn.
Start of landing burn.
Stage 1 landing leg deployed. Stage 1 landing confirmed.
And as you saw and heard, we had successful first stage landing at landing zone
Stage 2 internal
4,
guidance.
which marks the second landing for this specific booster, which previously supported NROL 126. This marks the 397th landing of an orbital class booster. Next up, we're expecting the shutdown of the second stage MVAC in about 10 seconds from now.
Stage 2 FTS has safed.
Da, man sieht uns, hello, you see our deployment container
Nominal
with the
parking
TO
orbit.
logo and Exolaunch logo. So
We just had
now we
successful
are
cutoff of our
waiting
second stage
for
engine, and we heard the
the
call out for
deployment
good
in
orbit.
about, I think,
Coming up next,
45
we have the
minutes.
second burn of our
And if
MVAC
we are
engine
lucky,
on
we
board
will
the second stage, or
see,
SES-2, around the T plus
InnoCube
50 minute
actually
mark.
being
After that,
deployed
the first
when
batch
we
of
have this
deployments
nice
will
camera
begin
view.
at about T plus 54 minutes.
For
We'll be
now,
back in
we
about
will
40
take
minutes
a
to bring you live
short
coverage
break.
of
We
SES-2.
have to
Until then,
prepare
enjoy the
the
space
mission
views, and we'll see you back here
control
soon.
center for our first contact, and we will have the live stream still on, and you'll see the second stage going to the orbit, and then we are shortly before the deployment. We will come back and moderate a little bit more, and hopefully see a successful deployment of InnoCube. So yeah, thanks for tuning in, and see you later when the deployment is ongoing.
Welcome back to our coverage of the Transporter 12 mission. We've had a great mission so far. We had an on-time liftoff at 11:09 a.m. Pacific time. We recovered the particular first stage for this mission for its second time, which landed today at Vandenberg's LZ-4. We're now about 40 seconds away from the second ignition of our MVAC engine on the second stage. While we don't have a view right now, we are expecting to have views of this. We do have views back, but we are waiting for confirmation of good orbit.
Nominal orbit insertion.
So there we just heard we had confirmation of good orbit insertion, and we had a successful second burn of the MVAC engine on the second stage. As a reminder, there will be a total of 101 deployment events today. We are on track to start these deployments in a few seconds from now. Apologies. We are on track to start these deployments in about 2 minutes from now.
GSAT Gen 1, deploy confirmed. Edison 1, deploy confirmed. Bro 16, separation confirmed. C Ops Otter, separation confirmed. Buzzer 1, separation confirmed. HCT Sat 1, separation confirmed.
Okay, we are back here. The deployment already started. We are about to be deployed in like, I think, 8 more satellites.
4G19, separation confirmed.
We are at 8, we will be deployed at number 15.
Scott, separation confirmed. Lime, separation confirmed.
This is our container here in the front of the left.
Falcon 1, separation confirmed. Falcon 1, separation confirmed. Tech Ed Sat 22, separation confirmed. Flock 4G 31, separation confirmed. Flock 4G 31, separation confirmed. PawSat 1, separation confirmed. POSAT 1 separation confirmed. ISL 46A CS1 separation confirmed. ISL 46A CS1 separation confirmed. InnoCube separation confirmed. InnoCube separation confirmed.
Okay, we are separated.
25 separation confirmed.
Whew. That was a relief for everyone here.
Elevation 1 separation
So
confirmed.
I think we can answer some question now, which played up, and
Flock
then
4G9
we
separation
will
confirmed.
again fade out and do the preparation
Flock
for our first contact.
4G23 separation confirmed.
So what questions we have? The question is in which container was the InnoCube transported to the launch site. In the end, we implemented integrated the satellite in Berlin in this launch container, and then it was shipped within the launch container to the launch site.
Separation confirmed. Flock 4G35 separation confirmed. Flock 4G35 separation confirmed. Paris T1 separation confirmed. Paris T1 separation confirmed.
The other question is now when we expect the first contact with InnoCube. So now the satellite is deployed and will switch on in about 30 minutes. And at about 22:50 Berlin local, so 21:50 UTC, we expected AOS and first contact over Berlin with InnoCube.
AE1C separation confirmed. AE1C separation confirmed. Answer LS separation confirmed. Answer LS separation. GSAT 45 separation confirmed. Block 4G15 separation confirmed. Block 4G15 separation confirmed.
So now we will wait until the contact time. So the team will start to prepare setting up the ground station and all the settings that we can acquire the satellite. We will update the trajectory that the antenna can track the satellite, and also rehearse our procedure for the first contact. In the first contact, we expect to command the satellite to start up, send telemetries, and we will check out the health state of the satellite. And as far as we can, it's a 10-minute contact about. So, and then when we have contact, the checking out of all the systems will be performed over the next days, and then
hear callouts as the payloads are being deployed. So far, we have had confirmation of 35 payload deployments.
Offset FO 19 separation confirmed.
35 payload deployments.
Aurora Tech Forest 3 separation confirmed.
So
Block 4G16 separation.
we have another question. What would we do different from the things we learned during the development if we have the chance to redo something? So I would say I would redo the cable channel. We have, of course, there were some small holes, and putting the electrical cables around was a pain in the ass at some point. So unless we can't do power transfer wireless, I would probably redesign a little bit parts of this structure. I don't know if anyone else, any comment on this or on another thing he would do? Someone wants to join in? I have a microphone. No? The people are already starting to prepare. The delay of the launch by 20 minutes and needs some readjustments. So we are starting to reorganize our procedures and the timings.
So maybe there's another question from the chat, maybe for all the team, maybe someone can answer. The structure of the InnoCube looks interesting. How was it designed and who was responsible?
So yeah, I can join in, I think, again. The structure was designed we had in mind that we have this modular system and this wireless system, so we wanted to have the structure as flexible as possible, and so it ended up to be like a CD rack kind of style where we can slide in the PCBs. And it was actually also designed with students. So we had 2 working students which did it during their thesis and during their working student worker time in the institute together with the researcher team.
So then there's another question from the chat. How long is the time in contact and how often are you getting contact each day?
So the next contact, or our first contact, is about 10 minutes. And usually we will have 2 contact windows per day. That means like we have in the nighttime now a contact window, and then in the morning a contact window, and this usually is in this latitude here in Berlin about 3 contacts, different lengths, but in some we have like about per contact window 15 to 18 minutes contact time. It split it up between the 3 contact windows, and then so today the contact window is relatively bad. We have a quite good contact now as a second contact, which is this 10-minute contact, but the contact after is only like a 2-minute contact, and the contact before we can't get because we are just separated from the rocket, was a few minutes longer, I think about a 5 to 6 minute contact. I don't have the timings right now, but about this is the contact windows we have. And I see no more questions. I think now we will dial down on our side again. You can silently watch us if you still want us. But now the team will focus on the preparation for the first contact and also performing the first contact. We won't do any moderation anymore. We will probably, like after the first contact, give a small feedback and then end the stream. Thank you for listening in, and it was a pleasure to host you here and to experience this event with us. So have a good night if you don't stay.
Fusion 1, separation confirmed. CG, separation confirmed. 30, separation confirmed. Flock 4G18, separation confirmed. Flock 4G27, separation confirmed. JC, separation confirmed. Flock 4G1, separation confirmed. JD2, separation confirmed. Flock 4G28, separation confirmed. Ion SCV, Amazing Antonius, separation confirmed. Lyra 1, separation confirmed. Flock 4G11, separation confirmed. Varda's W2, separation confirmed. Ray, separation confirmed. Ion SCV Eminent Emmanuel, separation confirmed. Flock 4G12, separation confirmed. Flock 4G5, separation confirmed. Flock 4G6, separation confirmed. Flock 4G7, separation confirmed. Flock 4G8, separation confirmed. Flock 4G2, separation confirmed. Flock 4G4, separation confirmed.
MBZ-SAT, separation confirmed.
So that brings us to the end of our first deployment sequence. Next up, we're going to coast until the third MVAC relight, or SES3, which should occur at about T plus 1 hour and 41 minutes. Until then, enjoy the space views and music. Welcome back to our coverage of the Transporter 12 mission. We've had a great mission so far. We had an on-time liftoff at 11:09 a.m. Pacific time, recovered our Falcon 9 booster for its second landing at LZ4, and completed 2 second-stage burns. We also completed our first deployment sequence and have another deployment set of deployments coming up. We are about a minute away from the third relight of our MVAC engine for roughly a 1-second burn.
Nominal transfer orbit.
And that's confirmation of a good orbit following our third burn. We'll take another break before the next batch of payload deployments begins at about T plus 2 hours and 17 minutes. We'll come back just before the fourth relight of the MVAC engine, which should occur about 2 minutes before the next deploy sequence. See you then.
welcome everybody. I'm happy to introduce you.
We're back to the Transporter 12 mission progress, and just about a minute away from the fourth
Nominal
relight
orbit insertion.
of our MVAC engine on the second stage. We actually just had a good call out there telling us that the fourth relight of the MVAC already happened, and we are in a good orbit. Followed by this will be the next batch of payload deployments. And as a reminder, today we are delivering 131 payloads across 101 deployments, including CubeSats, microsats, and orbital transfer vehicles carrying 30 of those payloads, 14 of which will be deployed at a later time. We have already deployed the first batch of 79 and have 22 left to go. So that next payload deployment sequence beginning in about 2 minutes from now. If you're interested, a full list of payloads are on spacex.com/launches. If you're not familiar, our transporter missions are dedicated rideshare flights to sun-synchronous orbit. There are always some really neat payloads flying on transporter missions, and today's mission is no different. SpaceX's rideshare program was expanded to accommodate even more small sats looking for rides to orbit. Falcon 9 launched its first 2 bandwagon missions previously, a separate line of rideshare missions that will deliver spacecraft to mid-inclination orbit rather than to transporters' sun-synchronous orbit. We have a pretty sweet view of the Earth behind our payload stack.
Connect to IoT7, separation confirmed. Lima 2, my name is Jeff, separation confirmed. C up SatGus, separation confirmed. Firefly 3, separation confirmed. Centauri 8, separation confirmed. Heo 01, separation confirmed. Lima 2 Wilson, separation confirmed. Connect to IoT 8, separation confirmed. Lima 2 Star Fox, separation confirmed. NorSat 4, separation confirmed. Lima 2 round tripper, separation confirmed. Centauri 7, separation confirmed. ISI 1, separation confirmed. ISI 2, separation confirmed. ISI 3, separation confirmed. Lima 2, Ariana, separation confirmed. ISI 4, separation confirmed. Firefly 1, separation confirmed. Connector IoT 5, separation confirmed. Connector IoT 6, separation confirmed. Lima 2, Alicia, separation confirmed. Firefly 2, separation confirmed.
We've had some beautiful shots of payload deployments this past in this sequence, and that brings us to the end of our second deployment sequence. And with that confirmation, we've successfully deployed all Transporter 12 payloads. We would like to thank all of our rideshare customers for entrusting us with their spacecraft today, a staggering 131 payloads across 101 deployments, including CubeSats, microsats, and orbital transfer vehicles. We also want to say thank you to the Range and Federal Aviation Administration for their support, and to you, our viewers. This launch marks our 7th mission of the year and 12th dedicated smallsat rideshare program launch. To date, SpaceX has launched more than 1,100 payloads to orbit for more than 130 customers across our entire rideshare program. If you're interested, a full listing of today's payloads can be found over at spacex.com/launches. And for more launch coverage, be sure to check that same site for the most up-to-date information. Thank you, and we'll see you next launch.
Aber ja, das Problem ist nur, wenn wir die Docker-Container neu starten, wird alles
Stehen alle vor.
Genau, genau deswegen würde ich die jetzt einmal speichern und dann können wir nochmal nach einem Fix.
Glückwunsch.
Danke. Ich muss noch mal ganz kurz eine Abmoderation machen.
Deswegen,
Darf ich einmal noch ganz kurz
deswegen
hier
machen wir
rein?
das am besten. Dann können wir das einmal vorne machen. Das hat einfach geklappt, so wie es soll. Der funktioniert erst da oben.
Kann ich einmal ganz kurz noch meinen
Nicht
Stream?
alle. Also es hat deutlich besser empfangen, als wir empfangen haben, war meine Meinung. Wir haben deutlich besser empfangen. Das Satellit hat deutlich besser empfangen, als wir empfangen.
Benny will noch mal kurz eine Abmoderation für den Stream machen.
Kurz ruhig sein, bitte. Ja? Ja. Ist okay. 1, 2, 3. Ich nehme deine Worte. Yeah, hello, one last time from Berlin. We established successfully contact with InnoCube. Great job from the team. Everything went as we expected. And yeah, thanks to the team, thanks to you who watched us. And we will continue tomorrow and checking out the satellite. And yeah, follow up us later to get the research results. Thank you for joining us and have a good night. And we will have also a good night and probably a glass of champagne too. Bye bye.